So am I audible to you? Okay, so if I am audible, I will start. I hope you can see my presentation. So I would like to thank MIT University and Department of Chemistry for inviting me for this talk. And I will just start the topic. So I will discuss in this talk about the basics of NMR, and then in the later part I will discuss some applications where I myself worked on that, and it will be interesting for you also to see them. So I would like to apologize for joining late because there was a connection problem, and earlier I was engaged in the classroom, so I could not join early. So for that, I am apologize to all of you. So I hope you can see my presentation, and I would like to move forward. And so NMR, we will do some basic regarding this, and then move forward. So in NMR, we use this setup, and in this setup, I hope you can see this. This is the way in which we store our NMR magnet, and here this is the big cylindrical form, missile-like structure. So it has most of the N2 liquid nitrogen filled inside it, and in the center, just center part, we have helium, and there is a probe which is used to record the signal, and at the top we have a arrangement to add sample, and if we do its enlargement, we can see here in this side there is a sample tube that is made up of quartz glass, and there is a that spinner is helpful in spinning the sample and putting it inside the probe at the right position, and this signal generated is then stored inside the computer, and with the spectrum. So we can see a spectrum here on this monitor. Maybe it is not so clear for you, but this is the way in which, and this is the again setup of NMR, but this is the old version which were used earlier, and continuous wave, and this is the pulsed NMR that was developed later and is extensively used in these days. And this is the same setup, but there is a different way of acquiring the signal here. But most useful and most widely used part of NMR is this, which you can see this instrument that's fully transformed. So now I will, why I given this, because here you can get some idea, okay, where we get NMR and how the instrument looks like. So now we'll go to the basic part. So I will discuss first introduction. In introduction part, I will do the physical origin, and then we go to the measurement, how it is measured. So Rabi, first of all, told about this interesting phenomena, that is spin can be seen, and it generates a magnetic field. So it is an internal property of the particles, and when we see spin, then we see, for example, electron. So when electron revolve or it moves in a other part of the atom, then it generates a magnetic field. So this has magnetic field has two, you can say, part, and north and south pole, and protons and neutron both have spin half. I'm talking about the proton and neutron because the NMR phenomena is associated with the nucleus. This is not associated with the electron, which we study for our experimental purpose or for the applied purpose which we are using. So here there is some combination of nuclei with their unpaired protons, and these protons have net spin half, and for proton we have a very high value of the magnetogyric ratio, that is around 42, and it is very highly abundant nucleus. Its abundance is around 99%, about 100%, around 100%. So it is the most widely studied nuclei in the NMR. Then we go to the another isotope of hydrogen, that is deuterium. So it also has a one unpaired proton, and its net spin is 1. So this change the whole spectrum. If we see later, the deuterium spectrum is a quadrupolar nuclei. Deuterium is a quadrupolar nuclei, whereas proton is having one unpaired proton, and it has net spin half, so it is non-quadrupolar nuclei. And again, we can see other combination. So there is a general rule that NMR active nuclei which has spin half or greater than that will be show up in the magnetic field or will show the NMR response, whereas those which have even atomic number and mass number, they will not show magnetic signal. So their average or their overall value for the spin is 0. So carbon 12 is NMR inactive, whereas carbon 13 is NMR active because it has a net spin half. But see, unfortunately, its abundance is very less. So when we want to record the carbon 13, then if we look at the abundance, it's very, very less abundance. So if we want to acquire a signal for carbon 13 for the same sample for which we are recording the proton, then we have to invest a large amount of NMR time to record the carbon 13 as compared to the proton. So proton can be acquired very easily. So the NMR instrument, which is at present in MIT University Gurgaon, is a low field, and that is not a high field NMR, but we can use it for a recording of proton and for carbon 13 and for fluorine also. And we can use them for signal identification for the normal acquisition of the signal. Complex nature of experiment we cannot perform on that, but we can record carbon to useful also the Yeah. So screen is visible. So I will continue with the slide. So we were discussing about the spin half system. So uh, as you can see that spin half system shows very simple system in NMR. So it represents all the nuclei that has spin half, and when we have a isolated nuclei with spin half, and then it kept in the magnetic field, then what happens? There is a transfer of uh, nuclei from their low energy polarization to high energy polarization. So you can see that on the slide, if you click once, the nuclei will shift from uh, its ground state energy level to the excited state, and that is happening by absorption of the radio frequency region of radiations. And this can be shown by clicking on the slide again, and then you can see these will go back to the ground state, and this will emit radiation, and that radiation will be dissipated to the surrounding in the sample. This can be viewed in a simple half system for understanding. And if you go to the next slide, then you can see that spin half, it is an internal property, and external factor are there which affect this shifting. And there's a term which we use in NMR, that is chemical shift. And chemical shift is the difference of the frequency of that particular nuclei to the reference. And you can see that in the next slide, you can observe. I will show this in the next slide. Okay. Okay, so this is just to show you the give you idea of large molecule where you can see different kind of chemical shape and isotropy on the same slide. And if you move to the next slide, okay, so here you can see again in equilibrium. You have to click on the slide again. So it is animated. So at equilibrium, there are random nuclei which are present, but when we put the system in the magnetic field, inside the magnetic field, then what happens? There is some ordering that is happening, and that ordering is happening due to the applied magnetic field. And we say this there is a equilibrium that is generated, and this equilibrium is shown by a big vector in the B0 direction. What is B0? B0 is the applied field in the Z direction, and we say this is B0 applied field, which is static, which is not changing. And when we put our NMR, we want to record the NMR signal, then what we will do, we will apply another field V1 that is generated through the help of software in the computer program, and that RF field in the form of RF frequency is sent to the probe, and that probe add on a new field V1 that is perpendicular or that has an angle 90 degree to the Z direction, and we say that is pulse angle 90 degree, and that shifts B0 to B1. So if it shifts B1 to B0, then what is happening? Our resultant equilibrium magnetization, which was in the Z direction, that shift to the XY. And when this equilibrium restore, then what happens? You can click to and go to the next slide. This is the B0 field, and then
Sir, I think your slide
there
is
is
not
M.
moving.
M is the magnetization that is
Sir,
revolving.
sir, am I audible to you?
Yeah. Yes. Yes.
I think your slide is not moving, sir. You are on which slide, sir?
Slide is not.
Right now, I can see physical
Spin half
organ.
system.
No, sir.
JQA solid state NMR spectroscopy.
Sir, I can see you are on
So
physical
we are
organ.
on the.
You have to unshare and share again your presentation.
So you are not able to see me, see my slides again?
So I can see your slide, but your slide is not moving. You have to unshare and share again.
I have to reshare again.
Right, right.
Okay, I will go to it and more here.
Sir, I unshare from my side. You just share again.
Okay, I will share again. I have also sent my presentation, so you can also okay.
So you please share again.
Yes. Sure. So, are you able to see now?
Now it's fine, sir.
No, it's fine. So I am on the
Yes, sir,
slide
please
where I can show the chemical shift.
Yes, sir. Yes, sir. Please continue.
Okay, so we were talking about the spin half system, and I will skip this to the next. Okay, so inside the atom there is a revolution, or there is a movement of the proton, and in the nucleus and electron, so they generate their own magnetic fields, and depending on that, the effective field that is felt by the nucleus is varied or vary, and depending on that variation, we can see the change in the different reason in the signal, and that is represented in the form of chemical shift, and this chemical shift can be represented by the delta here. I hope you can see this, and this is the general formula we use for the measurement of the chemical shift. So if I move forward, so okay, so I hope you are able to see now this slide. This is showing I was discussing last time this slide. So there is a shift of the nuclei by applying the external radiation, and that radiation change the equilibrium, and that equilibrium change can be shown by this way, and this change is carried out with the help of RF pulse that is generated through the computer system, as that is attached to the NMR spectrometer, and that can be calculated theoretically, and then we apply it depending on the system. And for proton, for example, we apply this and we get a signal by shifting the equilibrium at 90 degree to the left frame or the z direction in which static NMR, static magnetic field is applied. So I was on this slide, V0, and there is a M. M is the direction of the effective magnetic field, that is after the equilibrium disturbance. So there is a frequency at which this magnetization vector is revolving around the applied direction when it reaches from non-equilibrium state to the equilibrium state. So this frequency that when there is a equilibrium will be shown by omega 0, and when it is not in equilibrium state, then this is shown by omega. So omega is represented by gamma into B, and where gamma is the magnetogyric ratio and B is the magnetic field in that direction. Okay, so you can see this. I hope you are able to see the spinning of the there is a gyroscope that is spinning. So it is showing that how the NMR signal that is generated behaves by disturbing the equilibrium, and when it goes back to the original state, before that it revolves around the applied static magnetic field direction, that is z direction, and it is going back to the equilibrium state. So it do a precession around this, and this is called precessional frequency, and this is also called as Larmor frequency. So that is characteristic for every particular element that is NMR active, and for that nuclei that is specific. I hope you can see this. Now, if you move to the next, then we can get a maximum signal when our system is in equilibrium. So when resonance condition met, omega and omega naught both are equal, and we get a maximum signal from that system. So I hope this is explanatory. If you can see this, there is a spin half system, and there is H nu naught, that is the value of the magnetic electromagnetic radiation that is absorbed by the nuclei to change its spin polarization. And this spin polarization is changing from uh, ground state, ground state to the excited form, or I should say to the non-equilibrium state. So if we compare NMR with other spectroscopies, I hope you are all seeing this slide. So there are different kinds of spectroscopy in which we deal, but in NMR, the radiation which we use is very, very low amount of energy, and we say this is the nuclear spin or radio frequency region, which is used in the NMR spectroscopy region. So if we move forward, you can see quickly here all the concept together. So a nuclei, when no magnetic field is there, and then we apply the radio waves, and B0 is the applied field, and it makes them polarize and a spin lower state to the spin higher state, that is alpha to beta state, and this can be represented in this way. And we can calculate Larmor frequency by a calculation of gamma, V naught, and 2 pi. And this is very important in NMR spectroscopy. Now, there is one more thing in which NMR is different, that is the population. So at room temperature, the population difference between the energetically higher state to the lower state is not very much. So at room temperature, the Boltzmann population difference is very, very less. So we have to do a lot of work to create a population difference here so that we can get a appreciable amount of signal. In the other case, well, at the room temperature, whereas with respect to NMR, this is not as good. Now, the effect of strength on the NMR spectrum is also very important. So as we move from, and due to the rise in the energy difference, and we can see the signal which are very near to each other at 300 megahertz, far to each other appreciably at 1600 megahertz. So here, if we want more resolution, we have to go from very from higher magnetic lower to higher magnetic field, and as we move to the higher magnetic field, we can see different region which were merged earlier, they separate out and we get a greater resolution. So during the irradiation, quickly, so what happens, it is in equilibrium in the z direction, and it can be shown by m naught. And when there is a application of the irradiation or the field, then what happens, this m0 changes from applied direction to the other direction, and when we apply a pulse, then it goes to the xy plane and then it comes back. So here is the xy plane, and when it goes back, then it precesses around the z axis. So this is, and you can see the 90-degree pulse will change the magnetization from the M0 Z direction to the XY plane. Now, what happens after we stop the irradiating the sample? We are not sending any pulse to the sample. Then what happens inside that? So when we are stopping the radio frequency pulse, then what happens? The signal which we are getting, that start to decay. The magnetization which was in XY plane, it recess and it want to again re-establish the equilibrium, and it again goes to the Z direction, and pictorially we can show here. So it is in Z direction and then it is XY, from XY to again Z, and it happens like a cone is rising from the XY plane to the Z. So this phenomenon is called relaxation. So in XY plane, the magnetization that disperse and goes back to the established, and this re-establishment of the equilibrium is so this re-establishment of the equilibrium is shown here. Now, so how pictorially we can show the function of the so this approach visible to you. Presentation visible to you? So I hope we have reconnected again. What is happening? Signal that was shifted to the XY plane, it goes back to the, yeah. So if you are able to see, then it's very good. Okay. So here you can see the generation of MXY. So MXY represents signal of the particular sample that is generated in the, and it shows how it looks in the XY plane. So it's decay like this, and this particular decay is characteristic, and this characteristic decay is called free induction decay in NMR. So if there is no relaxation, the real case with relaxation, if you can see two curves here, so this is showing the decay of MXY, but it is actually not decaying, it is just evolving, and here it is decaying with the time. So this decay with the time is known as a free induction decay, where here there is no decay. So this decay is caused by relaxation, that is called T1 relaxation and T2 relaxation. And these are very characteristic for a particular nuclei in a sample, and they gives a different kind of information to us. So now if we see a signal accumulated on the NMR spectrometer, it will look like this. This has many frequencies inside that. This signal accumulated depending on the nuclei, and this is called as free induction decay. And when we Fourier transform this, then it generates a spectrum, and that spectrum is called as a NMR spectrum. And Fourier transform is a mathematical way to convert a time domain signal to the frequency domain. So this is done with the help of NMR software, which is available with the NMR spectrometer. And in Bruker spectrometer, we have another JSON software which is used, but the underlying process is the Fourier transform. So now there are chemical shifts, which is very important in the chemistry or for the chemist point of view. And these chemical shift or has origin that is related with the induced chemical shift that is generated by the electronic environment around the nuclei, and that electronic environment around the nuclei generates induced field. So that induced field may be in the direction of the applied field, then it reinforces the signal, and it will generate a signal that is a de-shielded if it is in the same direction, and if it is in opposite direction, then it will de-shield. Then I should say de-shielded signal occurs at lower magnetic field as compared to the normal one. And if it is in the same direction, so then it will generate signal in the very higher field style. So if we see it is a chemical shift, for example, from 0 to 15 for the proton. So in the 0 side, there is a higher magnetic field strength, whereas in the other side, 10 to 15 side, if you move away from the 0, then it is de-shielded. So acid anhydride, aromatic amides, alkenes, so they are far from the 0. So it means they have more less magnetic field. They resonate at very low magnetic field as compared to aliphatic alcohol protons and ketones. So that is the characteristic of the compound which helps that shift in the opposite direction. So there is another part of the all which I discussed, that was basic, that is applicable to both the NMR, that is it is if it is a NMR is liquid state or solid state. So there are two kind of NMR, liquid state and solid state. So in solid state NMR, we have a very broad signal, and like this is the signal above red line you can see in the static, and the lower is the signal which you will get if your sample is rotated inside the magnet with very high speed, which is called MAS. And there are interactions which are very dominant in the solid state, but in solution state, these interactions are absent. And if these interactions are absent, we say that they are isotropic in nature. So in solution, what happens? Due to the molecular tumbling, there is a narrowing of the line, and we get a very sharp spectra in the solution state. Whereas in solid state, we get the spectra which are broad without spinning the sample, and if we spin the sample, we get a very sharp peak, relatively sharp peak. So this example of carbon 13 NMR, tyrosine, you can say a red color, very broad signal, and blue color, that is a very sharp signal. So now I will move to some applications so in which our lab was working. So as we know, I am skipping the slides because we have a lesser time now and due to many interruptions. So I will focus on the direct application. So we have a way to extend the lifetime, and that way is known as long-lived state or single state generation. So that is a method by which we can generate it, and they decay at a slower rate as compared to the normal NMR signal. And there is a recipe or there is a way to make them. So I will not discuss the detail of that. So I will go to the application. So we worked on the chemical exchange in NMR and where we use the singlet states. So come on to this slide. I hope you are able to see this. So if we look at the molecule here, this molecule has a partial double bond character around CN bond. So if you see here, there is a benzene ring, there is a partial double bond character between carbon and oxygen. So if you see here, the resonance condition, if you see, so NC bond is partially double bond character. So if it has two orientation, so where cis or n transform. So we have tried to measure this rotation around this carbon nitrogen partial double bond. So we have this signal for this. So directly we could not see this, but if we look on the proton on the benzene, we can see a spectrum like this. So here we have a spectrum where A form and B form, which I have shown here, is represented in this form. So signal B from A and B, they have a common area where the signal of two are merging. And exchange is happening in water also, in like NH and water system also, and in protein system. When we put them in water, there is also exchange between the proton or which are on the backbone in the acidic form or the basic form and the water. So measurement of exchange, very interesting phenomena. So exchanges of two kinds, slow or fast, and intermediate. So in slow reasoning, you can see distinct values of the signal of both the isomers which are present, and in the case of fast signal, you will get a average signal, fast exchange. So this is a simulated spectra to show you. And this is the middle part which is called coalescence. So we used here slow exchange rate measurement that's limited by T1. We used here LLS and also the conventional method. So here the spectrum you can see. So this reason we focused, we generated long-lived states between this pair of spin, and then we get a result that was very good for us. And here if you see, uh, there is a temperature and rate of exchange measurement that is done, and we get two kind of isomers, A and B, and then ratio also changes by changing the temperature. And we prove that okay, there is a existence of two isomer first thing with the help of NMR, and we measured the rate of exchange with the help of NMR by using the 1D selective inversion recovery. This is the way we use the pulse sequence for that. This is the pulse sequence for NOSI. So with the NOSI, we recorded this and we integrated the cross peaks, and with the help of that, by plotting with the mixing time, we got a curve, and from there we get the K exchange that is coming out to with like this 1.25. And we confirm this by using again another method, that is selective inversion recovery method. And here we got again value of rate of exchange and also the measurement at different temperature. So this is we did with the long-lived state method again. So there is a decay of the signal. One of the signal is inverted and another is seen. So by this we got this method, this data, and we got a appreciably good value of the rate with respect to the other method which we were using, and we were able to use measure the uh, activation energy of this particular process. I wanted to explain it more, but time is short, so I have to move further. So this is a summary of this work which we did. And then we also did on this problem. This was very late when I was doing work, the last part. So measurement of the interaction between the beta cyclodextrin and drug with the help of long-lived state generation with the help of NMR. So a good drug should have a appreciable amount of solubility. It should be safe, and there are other conditions which should be fulfilled. So beta cyclodextrin is used as a drug carrier. So the what is happening? So in the drug and drug carrier, there is a water molecule which are encapsulating it, and when we drug enter inside the drug carrier, then it forms a complex and a cased drug. And when this happens, there is a change in the NMR parameter. So we measured the relaxation time, and also we generated the long-lived states, and we compared them, and we then confirmed that, okay, when drug goes inside the drug carrier, how much amount of drug can be put inside the drug carrier, that can be measured by using the NMR method, which we did. So here is the structure, just to show you. There are 4 different drugs we tested, and this is the cavity of the beta cyclodextrin inside and outside. And here, this is the NMR spectra which we took for the drug and with the drug carrier. And there is a formation of 1-to-1 complexation with paracetamol, indomethacin, and 4-methoxybenzamide. So we started with the paracetamol, and then we extended to other drugs also. And what you can see here, okay, here. So in LLS spectrum of paracetamol and beta cyclodextrin, so there is a decay from 50 millisecond to up to 15 second. And in LLS spectrum, you can see it is still there. So LLS is long lived as compared to the normal relaxation time. So here what we did, we recorded these spectra, and then we plotted the mole fraction, that is singlet relaxation time. So what we see a pattern here, like after the half of the fraction, like 0.5, we can see there is a tendency to be a straight line. And after this, there is a very much change in the relaxation time. So after this, relaxation is almost constant. So from here, we concluded that there is a maximum drug load that can be done in the drug host is half, like 0.5, or there is a formation of 1-to-1 complexation. And we cannot confirm this by T1 measurement, because in T1, the change was not so regular. So we could not conclude from there, but with the help of LLS, we could do it. So why this was happening? Because when the drug goes inside the drug carrier cavity, there is a proton-rich environment. So it helped to relax them very, very fast. And that's the reason we got good relaxation time. And when there is a long-lived states, this relaxation time is extended. So this was the another application. So still there are many applications which I could show you, but due to the time limitation, I have to stop here. So for other time when I will visit there, or I get a chance to come there, I will explain the other thing also, and I will discuss the remaining part also. So sorry for the disturbance, but I could not improve the signal here. It was not so good what I was expecting. But thank you for your patience, and thank you for the help during this presentation. And I would like to conclude. So this is our NMR lab facility in IIT Delhi where I worked. So I would like to thank to my colleagues and Mr. Professor Narayan Purur, who is the supervisor and the lab in charge of NIT Delhi, Rutraj and other Panshu and Manjit. And I would like to acknowledge MIT University for inviting me and Central NMR facility and UGC for the help for the research funding, and my team members and my supervisor, and also to Dr. Gyan and Dr. Pooja for helping me during this presentation. And thank you.
Thank you so much, sir.
So I am listening. If you have any question or you want to ask something, I am here.
अच्छा इसी में कर जाता था ये बढ़िया बात पापा अरे मेरा कैमरा सब दिख रहा है इधर क्या नहीं मैंने तो चेंजेस नहीं होते हैं तो दे रहे हो तुम दे रहे हो सब फाइनल है और क्या चेंजेस कराने के लिए बाद में गाइड कराएगा चेंजेस जी हो जाएगा इसमें हो गया अच्छा ये तो बंद हो गया